Welcome back for week 7, where the topic of this week is divide and conquer. Up to this point, we've been doing some calculations of recursive functions using the master theorem to solve things, and we haven't really had too much opportunity for us to actually come up with some of these algorithms on our own. And the idea is essentially to divide the work and then to conquer it. So here is the simple idea behind that. You generally, in these cases where divide and conquer is applicable, have a problem that by itself is a little too hard to solve. But what you could do is take that problem and split it up into two or so basically more than one smaller subproblems. So we have a subproblem and a subproblem, which we then further subdivide by splitting into more subproblems. And eventually you get to a point where you reach a base case, somewhere where things are really simple to calculate. And there you can compute things very directly. With that result, you can conquer, combining them together and merging them back up and solving your subproblem using the answers that you've determined from all of the subproblems of that computed directly. And you sort of go back up the tree using the answers you've combined, and presumably by the time you get back to the top, what you have are answers to smaller subproblems that you can easily take and use to solve a trickier problem that you started with. So divide and conquer algorithms are very common, especially for recursion. So there's sort of actually three parts to this. I said it's divide and conquer, but really it's divide, conquer, and combine. Where the division part is taking it and breaking it up into generally two or more smaller subproblems. Conquer, where eventually the subproblems get small enough that you can just solve it directly. And then finally combine, where you have your directly solved answers and you can combine them together to give you the solutions to help you solve the original problem. So when is this useful? It's useful for what's called fast multiplication. Turns out the way that you probably learned how to do multiplication in high school is painfully slow and not good, and there are faster ways to do it. Sorting algorithms like quicksort, merge sort are definitely good applications for divide and conquer. Understanding terrible jokes is another good reason, and many, many, many more beyond just these. So here's a practice problem we'll talk about in class. There is an algorithm here that determines if a list is sorted. And so here is some code. Now tell me, is this algorithm correct? Is it not guaranteed to terminate? Is one of the base cases wrong? Are there sorted lists for which false is returned, or are there unsorted lists for which true is returned? If you're not sure, maybe try coding it and seeing if you can figure it out. Second practice problem is the exact same 5 options, but just for a different piece of code. So once again, give it a shot, see if you can figure it out. So in this video, I'm going to focus on a problem called maximum segment sum. This is a problem that is a pretty good application of divide and conquer, because it does involve all 3 of those steps: divide, conquering, and combining. So what's the idea here? We have an input, which is a list of numbers, and our problem is to find the maximum segment sum of that list. And so what does that mean? Well, a segment is a contiguous portion of the list. So if I have a list of, say, 1, 2, 3, 4, 5, 6, I can take 4, 5, 6, or I can take 2, 3, 4, but I can't take 1 and 6 and leave out the stuff in the middle. They all have to be connected. The maximum segment sum is the maximum sum of any of the segments you can possibly grab from the list. So the maximum segment sum of 2 minus 5, 8, minus 6, 10 is 12. And the reason it's 12 is because I can say I'll take the 10, I'll take the negative 6, even though it sucks, because I can then take the 8, and I have 8 minus 6 is 2, plus 10 is 12. And if I were to go over here, I would grab the minus 5, which tends to not really be worth it. How do you compute the maximum segment sum of a list? Well, we can do so using divide and conquer. And then once we've done so, divide and conquer, it turns out, is a perfect opportunity to analyze runtime using the master theorem. Now, let's start off by thinking about a problem, which is, what is the maximum segment sum of an empty list? Is it 0? Is it plus infinity? Is it minus infinity? Is it undefined? Something for you to think about. So here is a potential implementation of calculating the maximum segment sum. It's supposed to return the maximum segment sum of the list from the indices starting from the low to the high. Assume it's originally called on a non-empty list, and low starts at 0 and high starts at the length minus 1. Are there lists for which this does not terminate? Does it fail for 4? Does it fail for 4 minus 5, 6 minus 7? Does it fail for 4, 5, 6, 7? Now, let's talk about the strategy to actually solve the the maximum segment sum problem. So first we have to divide. And so what does that mean? We are going to figure out what the midpoint is of the list between low and high, so halfway through, and that's going to give us two smaller subproblems, the left half and the right half. And if we can find the maximum segment sum in one of those halves, that's going to be really helpful for us. Conquering means we're going to take each of those halves and find that maximum segment sum. To combine, we're going to look at the end at what is the maximum segment sum of one half, the maximum segment sum of the other half, and the maximum segment sum of the segments that specifically cross the midpoint. It could be you take like a little bit of the left side and a bunch of the right side, or maybe vice versa, and we're going to have to look at that as well. So when we're doing the combining here, what we're going to need to do is take the maximum segment sum that extends from the midpoint going leftwards, plus the maximum segment sum that starts from the midpoint going to the right. And if we can combine those together, we have the maximum segment sum that crosses the middle. So the code for that is going to look something like this, where we split it in half. We have left and right, and what we're doing is we're iterating through, starting from the midpoint and going backwards towards the start, so essentially going left, and on the other side we're starting from the midpoint and then going to the right. And while we're going through there, we're figuring out how far essentially can we grab through from the midpoint across until we've figured out the biggest we can possibly take. It might be the case we don't want to take anything. It could be the case that we want to take some amount of it, but not too much. And eventually we stop and say, okay, whatever amount we have starting from the middle going left is the amount that we're actually going to grab. And then we do the same on the other side with the right. And once we have our left sum and our right sum, we add them together and say that's the maximum segment sum that crosses the middle of this list. Given that, you have enough to write this algorithm. You need to do the divide and conquer, split things up, recursively call your function, and use the code from the previous slide, the max crossing code, to find the maximum segment sum of the whole list. With all the pieces together, I think that you can actually code this, and you should do so. Now, another practice problem for class. The worst case runtime for the correct divide and conquer maximum segment sum is what? Is it n? Big theta of n, big theta of n log n, big theta of n squared, or big theta of n squared log n. So now we're going to look at another problem, which is selection. Given an input that's a list of n numbers and an integer I between 1 and n, the problem is to return the ith smallest value from the list. So for example, if we have a list that's 6178 and I is 2, we want the second smallest number. The second smallest is the 6. That's what we're doing. All right. Now, given that problem, which of these algorithms that are here are going to help us a lot with solving in the best worst case time? So the optimal worst case time. Will a quick sort help us? Will merge sort help us? Will a function that finds and returns the minimum help us? Are more than one of those equally good, or none of these helpful? Spoilers, we're going to use the pivot idea from quicksort to help us out. So the idea is we're going to choose a pivot, we're going to partition the list around that pivot, and then what our list is going to have is stuff smaller than the pivot itself, and stuff bigger than the pivot. Now, given that, and suppose we want the fifth smallest element in a list of 10 elements, when we partition, suppose our pivot ends up in position 3. Where should we look for our target number? Do we recurse on the left side of the pivot and look for the third smallest? On the right side of the pivot for the third smallest? Right side of the pivot for the second smallest? Or are all of these wrong and it's something else? So here's some pseudocode that implements the selection or quick select algorithm. First off, if the length of the list is 1, we are basically just looking for the first number that's there. Okay, now suppose we have something that's a little less trivial. We are trying to look for the ith smallest in our list that's a little bit bigger than that, and we're going to partition our list based on a pivot x, and so it's going to be split into left, all the elements that are less than or equal to x, and right, all the elements that are greater than x. Now, if the length of the number of items in the left plus 1, basically the pivot, is equal to I, in other words, let's suppose we're looking for the fourth smallest number, right? And we find out that the size of our left list is 3. What do you think the fourth smallest number is? Well, the first three numbers that are there are all the 1, 2, and third smallest numbers. The fourth one's just going to be the pivot, so we can just return x. Now that's the lucky scenario, which probably won't happen too much. Suppose instead we have that the size of the left half is going to be bigger than what we're looking for. In other words, a lot of numbers are on the left, and we're looking for maybe the fifth smallest, and the left has 10 elements in it. Well, in that case, we're going to take our 10 elements and find the fifth smallest. So we just do quick select on the left and keep I as it is. Now, in the other scenario, the right side is bigger, and so what we're doing is instead we're trying to look for, let's say we're looking for the fifth smallest number, and we got some number of them that show up in the left side, like maybe 1 and 2 and 3 are on the left side, and the rest are all on the right, not including the pivot. Well, then what we need to do is we are quick selecting on the right side, and we're going to have to shrink down the number that we're targeting because we're not actually looking for the fifth smallest anymore based on the remaining numbers that are there. We need to exclude everything that's in the left side and exclude the pivot as well, and that changes our ith smallest that we're targeting. Now, let's suppose that the chosen pivot is the worst pivot you can possibly pick every single time. In other words, it splits the list into an empty list and a list of length n minus 1. In that case, for our quick select, is it in big theta of n log n squared, or n squared log n? Alternatively, suppose it's the best possible pivot. Is our code in big theta of n log n squared log n? So the last algorithm I want to talk about is called Karatsuba's fast multiplication. In other words, the idea is that being able to calculate two numbers, x times y, turns out there's a lot more behind it than just x times y. And if you think about the time that it would take you as a human to calculate that multiplication in your head when x and y are potentially very big numbers, can get really problematic. If I just asked you right now, without a calculator on paper, to compute 1,257 times 9,752, you would have to work that out using probably a very painfully slow process. And it turns out there's an algorithm that accelerates how quickly you can do things using a little bit of tricky math. So the idea behind Karatsuba's fast multiplication is that being able to multiply two numbers that look like this, 5,678 times 1,234, it's really, really chunky and annoying. If you had to do this on paper, you're cross-multiplying all over the place, carrying numbers. It's so much work. But with some really tricky math stuff, we can shorten the work down. First, we're going to split the numbers in half by the digits. So 5,678 is going to be split into A and B, where A is 56, B is 78. And so what we're actually looking at here is x is equal to 10 times 10 to the power of half of its length, so n over 2, times A plus B. So in other words, 5,600 plus 78. And the same thing goes for the other half, y. Now, if we break things up this way and we try to substitute in these little formulas for x times y, we get 10 to the n over 2a plus b times 10 to the n over 2c plus d. If we expand everything outwards, we combine these two, we get 10 to the n times a times c plus 10 to the n over 2 times ad plus bc plus bd. Now this, if you were to apply the master theorem at this level, and so bear in mind that our sub-problems are multiplication, and our combination is the addition. And so the addition here is not so bad, right? If we're adding these together, their length is proportional to our original n, so it's basically big theta of n to add this term and this term and this term together. Okay, great. But what about if we were to apply the master theorem and look at the multiplication? Well, how many multiplications do we have? We have 4. We have AC, AD, BC, and BD. And if you apply the master theorem, which I recommend you make sure you can do that, you find that this is big O of n squared, which is not really great. That's pretty much the complexity that you would have if you were naively just multiplying these together, cross-multiplying. For each digit, multiply by the other digit. Not really an improvement, but there is a trick we can do. And it turns out that you can't avoid the AC and the BD, But this part in the middle can be simplified. So if you take this and consider a plus b times c plus d yields AC, AD, BC, BD. Well, here's the thing though. If we're already computing BD and we're computing AC, we can actually just rearrange this and take our term in the red here, which is 2 multiplications, not good, and reproduce it as a plus b times c plus d, which is 1 multiplication. The addition here is not really too big of a problem, minus this we already know the answer, and this we already know the answer. So this whole thing is actually not too bad, just 1 multiplication, which means instead of having 4 sub-problems to solve, we only have 3. So at the end of the day, the recurrence we have instead of 4tn over 2 plus n is 3tn over 2 plus n. Apply the master theorem, we get big O of n to the log base 2 of 3, which is better than big O of n squared.